which I thought showed it.
Yeah, the long-term visitor, but I think a bit one layer. He's not a long-term visitor.
Okay, it's a pleasure to introduce the second speaker this afternoon, who also is my colleague at Cornell. Banerjee is a UT Aston graduate, was a postdoc at Stanford, I guess nearby here, though I don't know how often he came by exactly here. Not so much. But maybe recently he's coming more often, and I guess he's at Cornell. He's also going to be a long-term visitor of this program, or is a long-term visitor of this program, going to really be long-term here in the second half of the semester. And with this, I should let you dare to speak.
Great, thank you. Okay, perfect. Right, so thank you very much for the invitation. So I'm going to sort of be doing the third piece of this talk on societal networks on ride sharing. This talk is going to be a little different from the previous two in that it'll be less focused on the data, but much more on just what are the problems in the space of ride sharing, how we can model these, or at least how people I've been working with have been modeling these. There are various models for this, and we can discuss that somewhat. Where we are in terms of solving the algorithmic questions, but in some sense, there's a lot of open questions in this field, and I'm sort of looking forward to working with many of you all during the semester and hopefully think about some of these. The reason I put up these three other pictures is these were my collaborators on these projects, but also they're long-term visitors for this workshop. So Ramesh Johari, who was also my postdoc advisor at Stanford. Daniel Freund is not here today, but he will be around soon. You've already seen some pictures of him in David's talk. Theodoros Likoris is sitting back there. Please direct all the really difficult technical questions in his direction. And this was also work done with Carlos Riquelme, who was a student at Stanford when I was doing a postdoc there. But just a little bit about the genesis of how I even started thinking about these problems. So while I was at Stanford doing a postdoc, we started thinking a bit about problems in dynamic pricing with respect to ride sharing. And just sort of serendipitously, we happened to talk to some folks at Lyft, actually Chris Shawley, who is still getting coffee, or, oh no, he's right over there, was sort of really nice enough to invite us over to Lyft to talk about some of our ideas. And it turned out that the folks in the data science team at Lyft were also just starting to experiment with dynamic pricing, and were trying to figure out, okay, how should we go about this? And I spent, I think, 4 to 5 really, really fun months working as a consultant at Lyft. This is back in 2014, in the early days of dynamic pricing. And in fact, Daniel was also there over the summer. Some of these slides that I'll show are actually taken from the Lyft recruiting slides. And if anyone is interested in problems with ride sharing, please get in touch with Chris. I hear they're looking for lots of people to work on these problems. And I can assure you it's a lot of fun. Okay, so what am I going to be talking about once I get this on? So this talk is pretty much entirely on ride sharing. Some of what I will talk about will apply in general to vehicle sharing problems, including bike sharing, but there are certain features of ride sharing which makes it special and interesting. They are increasingly becoming critical components of urban transit. When I used to give this talk 2 years back, I'd still explain what Lyft and Uber is. Some people hadn't heard about it. And it's nice that as time goes on, my intro slides can get shorter and I can talk more about everything else. The reason I find it really interesting is I think ride-sharing platforms are truly a crucible for sort of the set of problems that I think about, and many of us here think about in real-time decision-making and operations management in general, but also in sort of algorithmic economics. So there are aspects of, like when I teach courses on pricing or on market design, I often find for most of the concepts that I'm trying to teach, ride-sharing is a great example. And at some point, I have to stop myself from using it as an example. But then the nice thing is, because these platforms are pretty much coming up from scratch, a lot of it is unexplored, and you can go in and actually try some ideas, and with a fairly short turnaround time, get these things implemented. So it is an amazing laboratory for people working in these areas to try out the theory in practice. I will still give a brief overview just in case there are some people who haven't used it. So what is a ride-sharing service? It's essentially a paired set of apps. There's one app for drivers, one app for passengers. This is what you see as a passenger. You sort of go into the app, you see a bunch of vehicles moving around, you request a ride. There are a bunch of different modes you can request it in. You can request a shared ride or a ride on your own or a bigger vehicle. Once you request it, you get matched to someone and you get shown a price. I'll talk more about this later, but essentially you get matched to a person, you enter your destination, that person gives you a ride, you get dropped off, you pay through the app. The entire experience is sort of mediated through the app. You give feedback, or actually both parties give feedback to each other, and that sort of completes the ride. So a very critical piece in the whole thing, and perhaps the piece which gets the most attention, at least in the press, is how these platforms do pricing, in particular how they do dynamic pricing. This used to be different earlier. So earlier what used to happen is you never actually found out the price. You could get a price estimate, but what you did find was this notion of the price multiplier. The way it works now, both in Lyft and Uber, is what's called upfront pricing. And the idea is that when you go into the app, you see an indicator of what's the current prime time or surge level. So here it says that right now, if you take a ride, you're going to pay 25% extra if you choose to take a ride. But at the moment you enter your destination and actually sort of, even before you request a ride, you are given a price upfront. So you're given a price, you can decide at that moment whether or not you pay it, and once you decide that, that's it. The price does not change. You could get stuck in traffic, etc., etc. The price is not adjusted. There are some caveats to this. There are certain other modes of working if you take a pooled ride, etc. But essentially, this is how the models work today. Yeah,
Quick framing.
yeah, of course.
This is testing the notion of what sharing now means in this situation. To what extent, in terms of numbers, how do the numbers of riders and car providers compare, and is there fluid flow between those two classes of participants, or is it, as I say,
So, okay.
there are quasi-professional ride providers?
Good. So that I genuinely don't know. We do have folks from Lyft and actually folks from Uber as well, and I have not directly worked on the data, at least for a few years. Yeah, I think I'll leave it at that. So I'll talk much more about, from a modeling perspective, whether the fluid versus the discrete matters. But in terms of what it is on the ground,
In there's a sense of symmetry of ride user and ride provider. Are those fixed roles, or do they change?
no, I'm pretty sure those change. So you do have people who are both users and drivers. And one way you actually see this a lot is you do see people switching back and forth between the apps, maybe to see the prices, etc., etc. So they do. So one thing people often ask about is, okay, what if you don't show the prices to the drivers? Will they ever find out? But then most people can sort of switch to the passenger mode and see the prices. So yes, so that there are, I don't know numbers on this, but I'm pretty sure there are people who use it in both modes. Not simultaneously, but at different times. Okay, so and just to sort of complete the story on what prime time or this dynamic pricing looks like, as of now, and I believe this may or may not be changing, but as of now, the prices for a ride are based on distance and time. So there's a fixed multiplier for distance and time. There are some additional fees for insurance, etc. But what you actually pay is the price based on distance and time multiplied by the surge multiplier. So this is what a receipt from Lyft looked like. This is actually quite old by now. This is 2 or 3 years back. Now it's a little more complicated, but at the heart of it, this is the structure. So this was someone taking a ride on January 31st at 12:35 a.m. Got a 25% prime time. I would actually say he got lucky in this. Okay, so what are, in some sense, the space of problems in a rideshare system? I'm going to kind of break it up into 3 separate pieces. So one large space of like real-time decision-making problems are concerned with mapping. So these ride-sharing systems have a huge amount of data from the GPS of the cars, and they're using it to sort of get better ETA estimates, of trying to estimate people's locations better and better. These things are actually really important for things like billing purposes, for example. You need to estimate the distances accurately if you're billing correctly. And so all ride-sharing firms have a large team working on problems related to mapping. The two sort of problems I'm more interested in are firstly problems related to logistics. So what I mean by this is sort of the logistics in terms of the supply once you've already accepted the demand. So once you've sort of committed to giving a ride to a person, you need to decide which car to dispatch. So here I'm kind of showing a hypothetical example where there are 2 riders who are asking for rides, and there's sort of 3 cars, and you're trying to decide, okay, who should go to whom. And the idea perhaps would be that by matching one driver to one passenger, you're sort of preserving drivers for perhaps more busy locations. So you want to think about how to optimize these dispatch decisions once you've accepted a ride. You can also think about matching. So this is sort of more to do with the ride pooling side of it. So both Lyft and Uber have a service where you can share a ride with one or more person. And in order to figure out what's the best way to sort of take the portfolio of rides that you have and match it up to people asking for it, it's a non-trivial combinatorial problem. And you need to do this really fast because if someone asks for a ride, you need to decide very quickly who should they be matched to. And perhaps the piece of it which captivates most people, or at least which for me is most interesting, is that even outside all the logistical problems in these systems, at the heart of it, ride-sharing systems are marketplaces. So they don't, at the moment, they don't have any drivers as employees. They don't, as far as we know, have too many autonomous vehicles. So at the moment, the supply is being provided by freelance drivers who are choosing whether or not they want to work on the platform. And what Lyft and Uber are doing is they're not sort of actually sort of taking some supply and matching it to demand. They're setting up the rules of a marketplace. So they're kind of, think of it as they're writing this notice saying this is what would happen if you join the market as a driver or a passenger, and then everyone's making a decision whether or not it works for them. And there are various ways in which this shows up. The 2 really interesting problems, at least for me, is firstly prime time pricing. How do you do dynamic state-dependent pricing in a ride-sharing system? And this is perhaps much more visible to most people. What is also more interesting, what is also equally interesting but perhaps less visible, is what are the levers you use to incentivize drivers. So how do you sort of incentivize them to drive at certain hours? How do you incentivize them to drive at certain locations, et cetera, et cetera. And what this talk is going to be about is essentially these 2 pieces. So how do we sort of formally model and think about logistics and market design? What are the algorithmic challenges? What do we know? Where do we want to go? And as I was saying, there's a kind of bigger ecosystem of on-demand transportation, which ride-sharing is a particular part of. So we already heard David talking about bike sharing. There are also some services where, like Car2Go or Zipcar, where essentially you have shared cars without drivers. So you have the cars parked at various locations in the city, and you can rent these cars for a certain amount of time. So they're a more on-demand version of essentially a car rental service. And what's common across all of these sort of modes of transportation in some sense are that they all have really fast operational timescales. So the number of rides per minute is much larger than, like, if you think of, let's say, an airplane pricing system, or the number of people looking for tickets for a single airplane versus, say, ride-sharing system, there's an order of magnitude difference in volume. But also what's really interesting about these systems is that they have very complex network externalities. So what I mean by that is, unlike in other sort of comparable systems, in a ride-sharing system, if you take a ride from one location to another, you've changed the supply at the source location. You've also changed the supply at some future time at the destination location. So you sort of, by taking one ride, you've affected the network at various points, and these sort of effects propagate through. And so when you're trying to think about how to control these systems, you have to think about these propagating effects. Or to some extent, you should think about these propagating effects and how much that affects your policies. There are also very different control levers than what we had before, dynamic pricing as before, but also how you can change dispatch based on current information, how you change incentives in a dynamic fashion, how you can pool demand together, etc. And there are newer challenges coming up. So as ride-sharing becomes more and more prevalent and people start accepting it, we need to start thinking about things like competition. So how does it matter that we have multiple rideshare providers? How are they interacting with each other? What's the effect of that on society? one thing which, at least for me, is really important is what is the effect of these systems on public transit. So ride-sharing systems sort of claim that they want to make transportation as cheap as water, but there is a feeling that there must be effects of that on public transit in general. And can we start sort of formally trying to understand what these effects are and what are the synergies between these systems? And kind of even more generally, what's the effect of having these systems on urban planning in general? Now, I'm not going to try to solve any of these problems, but sort of try to outline what I think are ways in which we can start thinking about this. So what does this talk about? So what I am going to talk about is a simple framework for trying to formalize these questions. So what's a sort of simple modeling framework for formalizing dispatch, pricing, rebalancing in a ride-sharing system? How does it incorporate things like data, state, and controls? And once we have that, what we've been working on right now is, firstly, how do you do approximate optimal control in these? So the underlying control problems are sort of highly non-convex and high-dimensional, but we have some ideas now on how do you do this well in certain approximate senses. And then secondly, and this was sort of the work I originally started off with, what is the effect of, what is the role of dynamic pricing in these systems? And kind of more generally, what is the role of market mechanism in a ride-sharing system? And my view of it is that the main, or perhaps the most important contribution of a market mechanism in the system is that it's a tool essentially for what I call algorithmic self-calibration. So although these systems are trying to learn demand and supply, there are certain barriers to doing that. And having these dynamic market mechanisms allows you to get over these barriers. And then I'll try to kind of conclude with some questions which I think are of interest, but I'd be interested in hearing what others think about. Okay. So the main challenge in any ride sharing or any vehicle sharing system, kind of, if I wanted to boil it down to one word, it is rebalancing. So any of these systems, by virtue of being on demand, they have non-uniform demand and supply across space and time, and you need some way of aligning the demand and supply in space and time. And there are kind of two high-level ways of doing it. So there is a sort of logistical solution, which is you try to rebalance this fleet, and David talked a lot about how that's done in bike-sharing systems. I actually took that diagram from Daniel's website. This is the sort of the demand-supply imbalances at a certain time in the city bike system. And you can see something similar. So this is actually a video of this car-to-go system. I think this is in Los Angeles. And what you can see is, for some reason, the video is not working. But what happens in this video is as the day goes on, you can see the cars sort of gravitate towards the downtown early in the morning, and then they get stuck there. And car-to-go and Zipcar actually have, or car-to-go, because they don't have fixed parking spots, they actually have people who manually go and drive these cars back. And David, again, talked about like the incentives for doing that. Now, the second thing is the sort of economic solution. So the incentives for moving these cars from the point of view of passengers, but also in the case of ride-sharing, incentives for drivers. So incentives to make drivers sort of join the platform at certain times or work in certain locations. And there are many control levers for doing this rebalancing. So pricing is the obvious one. I already talked a bit about dispatch. But increasingly, people are thinking about how, if you had empty vehicles in the network, how you would rebalance them. There are certain ways of doing this by nudging the drivers. So drivers get to see what are called heat maps, or in some sense, an idea of where the demand profile is, or something which looks like that. And they can self-choose where they want to work. But increasingly, as autonomous vehicles come into the mix, there's a possibility that you can genuinely control some of these vehicles and use these for rebalancing. Okay, so that's sort of the problem space that I want to look at. And so what I'll talk about in maybe the next 10 minutes is a simple model which captures most of these effects. It doesn't capture everything, and at the end of it, we can stop and sort of think a bit about what's in and what's not in the model before going on to the algorithms. So here's kind of my really simplistic way of thinking about what a ride-sharing platform is. And essentially, I'm viewing it as what's called a closed queuing network in stochastic modeling. So what's happening over here, what I'm trying to depict is, here's a network where you have 4 stations. So think of these stations as localities in a city. And each of these stations have a number of vehicles. So these are vehicles which are located in that same neighborhood at this current instant of time. So in this case, you have 4 neighborhoods. You have 2 vehicles here, 3 over here, 1 over here. And I'm going to assume throughout that there are n stations, and the total number of vehicles is m, and this is remaining fixed. So there's a fixed number of vehicles which are sort of distributed across this network. So at any instant of time, the state of the system is basically a point in this nm simplex. So it's a sort of distribution of m vehicles amongst n locations. And what I'm going to assume is that you have a stochastic stream of passengers arriving at different locations in the network, and in particular, the rate at which passengers show up at location I and want to go to location j is given by a Poisson process with rate phi j. We'll talk more about this later, but for the time being, so there is sort of a matrix of these arrival rates, and at each node you have these different Poisson flows coming in and wanting to go to different destinations. So what I've drawn over here in the dashed line is basically a passenger who showed up at this location who wants to go over here. And now the platform needs to decide whether or not it wants to serve this passenger and at what price they should do so. And so what the platform gets to do is they get to set state-dependent prices. So what do I mean by this? The platform can look at the system and go, okay, I have so many vehicles here, here, and here. Based on this, I feel you should pay so much for the ride. And so this price is offered to the passenger in the form of this upfront price. And then the passenger, I'm assuming, is sort of making an instantaneous decision. If they feel the price is good enough, they take the ride. So each passenger has some value for the ride. It's drawn from some distribution. If they're in the tail of the distribution, if the value is more than the price, they're willing to take the ride. And so what happens once the passengers matched up is the car starts moving. This typically will take some time to go from one location to another. For simplicity in this talk, I'm going to assume the travel times are 0. This is not critical. Okay, so here I have, so what happened here is we went from 3 cars over here to 3 cars in that location. Another passenger showed up. There is a car available, willing to pay the price. The car moves. So what happens if a car is not available? And I'm going to make an assumption that the customers are myopic. So what I mean by that is if someone shows up and they see that there is no vehicle available within a reasonable ETA, they just abandon the system. So maybe they switch the app, or they take public transit, they take a bike, etc. But from the point of view of the platform, they drop out. So that's one way in which you can have customers abandoning. The other way in which a customer can abandon is if you offer a price and the customer decides it's too high. It's not too cold, I much rather bike or walk. So that kind of pretty much entirely encapsulates the system. If you think, if you've had some prior exposure to thinking about stochastic models, just knowing which vehicle is located where is actually a complete description. You can sort of figure out the entire Markov chain of the entire sort of evolution of the system based on that information. And the objective that we are concerned with is optimizing some sort of long-run average system objective. So it's not obvious what is the target objective of these platforms. So the platforms do care about revenue for sure, but then given that they're just, in some sense, they're still sort of gaining traction and they want people to use it, the platforms definitely care about customer engagement, how many rides they're giving. And in some global sense, the ride-sharing platforms also care about are people happy using the system. So what is the overall welfare of both the drivers and the passengers in the system? But what I'm interested in is you give me a choice of objective, it may be a combination of these. I want to come up with an algorithm which sets these prices to optimize the long-run average of this objective. Okay, so that's pretty much the entire model. Pause if there are any questions, clarifications. Yeah, Andrew.
Maybe the way you deal with space, so you have these 4 locations, it seems like you've discretized space.
Yeah, I have. Okay, that's a great point. So yeah, I have. So I am assuming the network is partitioned into these discrete chunks. But you're right in asking, why did I assume that this person couldn't get a ride? Maybe that place was near enough. So actually that's a good place to sort of start thinking about, okay, what are the control levers I have in some sense? What I talked up till now was just about pricing. So I can sort of deter or encourage people to go from one place to another just by increasing or decreasing the prices. So what I'm indicating over here is, in some sense, if I know that there's an unavailability of vehicles in these two nodes and there's an excess over here, I should try and set up flows which go from like excess to deficit by adjusting the prices. And that's kind of the main control lever we'll be thinking about. But another very natural control lever is, if there is unavailability, you can ask the question, maybe I can pull vehicles from somewhere else. And this is what is typically called the dispatch problem. And in general, the dispatch problem is more general. So if I have a passenger who's shown up who wants to go to some location, given a set of vehicles within certain sort of ETA budget, or I want to decide which one to pull, and it may be that when I pull one of these vehicles, because it's too far away, the passenger may abandon. So that's the sort of, that's another control lever which is actually after the pricing. So once the passenger has accepted the prices, I need to decide, or I need to, in parallel, decide the dispatch. The other thing you can model using pretty much the same setup is, how would you rebalance empty vehicles? So in this setting, suppose I don't want to think as much about the pricing and the dispatch, but what I really want to do is, whenever I have whenever I have unavailability, I want to take vehicles from an overloaded location and ask them to move. And as I said, there are ways of doing this using nudges, but I mean, in future, this could be an autonomous vehicle moving. The point, of course, is in order to do so, I need to incur a cost. I mean, there's a vehicle driving and I incur a cost of the miles. And in some sense, I want to use this model to think about all of these problems.
Question?
Yeah.
Point of clarity. You mentioned a single price. How does that work with the notion of this as platform or a market that brings together willing sellers and willing purchasers? Would there be two prices and a spread?
So what does the driver see? Yeah, good. So I'll actually talk more about the drivers in the second part of the talk. The short answer, as of now, and correct me if I'm wrong, the driver usually gets a fixed percentage of the price charged to the passenger. There's no underlying economic reason for doing that. It's arguably you should have a spread. From what I understand, there may be partially legal reasons for sort of having this kind of linear structure. So right now it is, if you give a ride, you get 80% or 75% of whatever the passenger pays. There are exceptions to this. The notable one is in ride pooling. So if you take, say, a Lyft line ride, you're getting a discount because there's a thought that you may be encouraging sharing down the line. And what happens, at least in the case of Lyft is sort of taking the risk upon themselves. So the driver is getting paid as if it was a single ride, whereas the passengers are paying a different amount, and the hope and the sort of the delta is being taken up by the platform. But we'll come back to the pricing in more detail later. So the first part of the talk will assume these vehicles are sort of given. It's like fixed supply. The non-trivial part here is that the supply is spread around the network and we need to move it around. So it's purely a logistical problem. Any other questions? Okay, so I guess I've been somewhat clear, or it's late in the day. So usually I get a lot of criticism at this point about the model, and I'm going to try and try and answer some of these criticisms early on, while admitting that there are things which are definitely outside the model. So firstly, okay, why even do this? Why even do theoretical models? We have these amazing systems. They have excellent sort of experimental infrastructures. Why not just try out different policies all the time? And to an extent, that is done. There's a huge amount of A/B testing which is being done by all of these platforms. But I would still argue that there's a huge amount of value in doing this kind of like formal modeling of these systems. So one of them is that the sort of scales and the real-time nature of these systems essentially mean that you must have very, very simple algorithms. So you can't be running something which is extremely complicated in the back end while simultaneously pricing like every minute for every location across an entire city. It's just not going to scale up. And so even if you think that there are complex controls which have a huge benefit, these need more resources. And you, in some sense, should be arguing, is the gain commensurate? So you need way more manpower to implement these systems. You need many more machines. You need better better communications. Is it worth the gains that you get? That's sort of a crucial question most of that theory hopes to answer. There's also the problem that even though these companies have excellent data science teams, in some sense there is always going to be some error in your estimation and forecasting. And you're then using these erroneous estimates and forecasts back in your model and claiming it's optimal. And you should be worried about, okay, how are these errors sort of propagating through? And there are certain things which are just very, very difficult to learn. So how do you learn what is a passenger's willingness to pay if you can only show like a fixed set of prices, or if you don't want to experiment on passengers, which it's unclear if the firms are actually doing price experimentation. But even just given that you have like 5 or 6 prices, how do you learn demand curves very well? And demand curves are easier to learn. How exactly do you learn a supply curve? How do you figure out why a driver is willing to work for certain hours of a day? There are sort of long-term effects in this which are just very difficult to try and extract from data. So that's what I'm sort of thinking of as known unknowns. And in some sense, having these models gives you a sense of how susceptible are you to these errors, or how robust are you against this. And then beyond all of this, there are sort of things which we just don't know about. These systems are extremely new, and they have certain effects on people which in some sense is outside the modeling framework. And by being hyper-aggressive about how we sort of control these systems, you may have certain side impacts which you didn't account for. Now, I don't mean to sort of try and jump on Uber and suggest that you'll delete Uber. So this was an issue close to a year back when there was a strike in JFK Airport, and Uber at some point actually decided that from what I understand, they realized that there was surge pricing, and they realized that this was not desirable because it was in reaction to a strike. And they actually turned it off and announced that it's been turned off. But interestingly, from what I understand, this was perceived as being anti-strike because by saying that you turned it off, you somehow suggested you were against the strike. I'm not going to take a side in this as someone who's actually helped design these dynamic pricing systems. There's a sense that these sort of problems can happen, and you need to be careful, or you need to have simple systems which you can understand and you know what these effects are, because else you may kind of get into these unknowns. So like you really need to understand what is the value of even just doing dynamic pricing, because you know people are getting upset about it.
Yeah. I mean, this one
I should move fast. No, okay, go ahead.
No, I don't mean to. This is more like, first of all, you're running on a day when there's a strike, and then now you're taking the surge pricing off to make it look like.
No, I mean, I totally see the optics of it.
Exactly. So
Yeah, but there's a sense that, which assumption in our model captured these optics? Or which assumption, these are really tough to think about, and in some sense, if you have simpler models and algorithms, you have some sense that this could still happen, but maybe you have some control over it. Okay, so that's why I think it's still, despite all the A/B testing and despite having this sort of excellence of experimentation and infrastructure, it's still useful to sort of think about formal models for this. Why this particular model? Why the stochastics? Now, in order to think about that, I'm just going to sort of go through what I think are the crucial assumptions. And there's a sense that none of these hold completely, but we do understand in some sense, how much our results depend upon these. So the first thing that I'm assuming is that there is what I think of as a time scale of platform operation. So there's some amount of time within which the number of cars, the arrival rates, the elasticities, all of these remain constant. So maybe there's the morning rush hour. We already saw these plots from David about the bike sharing system, but it was clear that this is not true. So there are definitely sort of time-varying behavior throughout the day, and it's an interesting question as to what's the effect of this. In practice, what you can do is you can take whatever the policies we suggest and resolve this whenever you think things have changed. But we have some thoughts about how our guarantees would change, but in general, that's an open question. What happens when you have time-varying arrival rates? I'm assuming that the number of cars. Oh, yeah.
I'm sorry. In your model, you had the number of customers or N was given?
So the number of vehicles was
M or
fixed.
N?
M.
One was the number of
No, so
potential
customers.
passengers, right?
So customers was a Poisson flow of customers.
Yeah, so, okay. So I'm unclear. So if the flow of passengers is given, I'm unclear what demand elasticities mean.
So when a passenger shows up, we can offer them a price, and they have...
Passenger showing up in itself would depend upon the price, right?
No, because you can see if someone opened their app to look for a ride before they saw the price.
I understand. But if I know that the Uber price is going to be half of what it was yesterday, I'm much more likely to open my app than after the fact.
Okay, that's completely fair. So I think maybe what you're pointing out is that there is a sort of longer term entry decision. Yeah, so right, exactly. So one example I knew of this was I knew this person at Stanford who used to go to Stanford from the city, and at some point of time he needed to make a decision of whether he would take his bike to the station or whether he would take an Uber. And in his case, okay, this was someone who thought a lot about experimentation, so he experimented. He sort of tried it for a month and saw how much it cost him despite the price fluctuations. But yes, that is one of the long-term effects which I think are just very difficult to capture. And in some sense, what I want to do is convince you that like dynamic pricing is so essential that we are willing to incur that risk. So
Yeah, I don't want to go beside the point, but I know there's a paper from Chicago which claimed that Uber's welfare benefit was $12 billion because it took this very short-term elasticity and said that was the long-term elasticity, right? Once I decide to take Uber, I'm willing to pay 50% more than otherwise, right? And so I think you can get very, very wrong
misleading
answers if you scale it up to...
Oh, I completely agree. So I'm assuming that there's a weak answer that in some sense the friction of checking your app is so small that before you head out of your home, just check your app. Maybe it's not expensive, but I completely agree there are long-term effects, which in some sense I'm sort of getting out of the model. There's also this, in some sense the model I talked about with the Poisson arrivals, it doesn't talk about bursts. So if you're at the 4th Street station in the morning and a train just arrived, you have a bunch of people coming out. They're not coming out in this nice Poisson manner. And this is the sort of thing people in stochastic control really like thinking about. What is the effect of this? What's the right way of pricing against it? I'm not going to talk about that in this talk. The second sort of timescale separation that I'm assuming is in that of strategic interaction. So what I mean by this is I already mentioned that I'm thinking of the passengers as being completely myopic. So they come in, they look at the system. If there's no availability, they leave. If the price is too high, they leave. They're not waiting around. They're not sort of playing games saying, oh, I'm going to look at it for 5 minutes and decide, etc., etc. So they just leave instantaneously. On the other hand, I'm actually going to, later on when I talk about pricing, I'm going to assume that the drivers are reacting at a very different time scale. So they're sort of sampling the system for a much larger amount of time and deciding whether or not it's worthwhile for them to work on the system or not. So there is a sort of intrinsic separation in the time scales. Some of this you can see from the data, but in some sense this I'm going to take as a given in the model. The thing which I feel is most troublesome about the way I set it up is I'm assuming a lot about the availability of data. So I'm assuming that you have perfect knowledge of the arrival rates, and as Praveen's pointing out correctly, I'm assuming a lot about knowing about the demand elasticities, and maybe I'm getting this completely wrong. It's difficult to learn, maybe this is changing over time. So is it really true that I have this information, and sort of more subtly, is it really needed to have all of this information, or can my policy sort of do well enough without this information? Yeah.
Checking on, you're still with the notion of just a clock ticking, non-metric clock ticking?
So I'm assuming everything's in continuous time, so it's a continuous time Markov chain with Poisson arrivals.
Okay,
So yeah, continuous time, discrete space. Okay, so this is kind of the first piece of what we can do with this model. This is joint work with Doris and Daniel on like how do we think about like optimizing the logistics in these systems. And just to recap what was going on, I had somewhat messy diagram, but just bear with me. So I have these flows of passengers, these Poisson rates showing up. I offer each person a price. The price could be sort of origin destination dependent. It could depend on the state of the system. Based on the price, the flow gets thinned down to some extent. And then all of these people show up looking for a ride. And I have these M vehicles at different points, and there's this flow of cars in the network which is set up due to the prices. And I want to try and understand, once I sort of fix a pricing policy, I want to understand how a certain objective behaves in steady state. So So why is this difficult? I'll try to sort of walk you through, so just what is complex about even thinking about this. So what I really want to do is I want to select a sort of thinning parameter for each pair of nodes. So for people going from I to j, I want to sort of decide what fraction of them to admit by choosing a price. And I can choose this as a function of the state of the system. So for every instantaneous state, I can choose a collection of prices. And these prices are going to induce some sort of long-term, like some sort of Markov chain in the system. And I want to try and maximize the expected reward added up over all pairs of origin destinations under this induced measure. So that's the problem I'm trying to look at. And this expected reward itself is not very nice, so it's kind of broken up into a bunch of parts. So firstly, I have to ensure that there's availability. If there's no vehicle there, I can't give a ride. This is the rate at which there are people showing up wanting to go from I to j. So phi ij is the sort of underlying rate, and then I've thinned it down by choosing a price. And then once both of these are met, I'm giving a ride. I get some expected reward from that ride, and I'm denoting that as this function I. So this is the expected reward I get if someone actually takes a ride to go from I to j. And I'm going to assume, yeah.
QE is the Q at equilibrium.
Q that's actually my control. So I'm choosing a price, and the price induces, so for every state, I say, okay, I'm going to let in, so right now there's so many vehicles, I will let.
X is, yeah, is the
instantaneous fraction of people I admit. Yeah, so the one thing I've swept a bit under the carpet here is instead of thinking about prices, I'm thinking about what fraction I admit, but it's sort of a one-to-one relation between these. And I'm going to assume that this function q times I of q is concave in q. This is not a very severe assumption. This actually turns out to be true for a lot of objectives you'd like to think about. So it's true for just the rate at which you give rides in the system, the sort of volume of rides. It's true if you just look at the economic welfare. It's true for the revenue function under certain regularity assumption on these capital Fs. So for many objectives that we care about, we know that q times I of q is concave. This turned out to be important. But this is still a really, really ugly optimization problem. So firstly, I'm going to sort of go back to the simpler notation, but no matter what I do, no matter how I dress it up, it's still the policy that I'm trying to choose is exponential size. So for every possible state of vehicles in the system, I need to choose this matrix of prices. So the huge policy space, it turns out that even if you sort of drastically reduce the policy space, so even if you say I'm not going to look at the state, I will just have a fixed price for every origin destination pair, now you're just looking at n squared parameters. But even then, this problem is non-convex. And it turns out to be non-convex in sort of really, really simple instances with like 3 stations and 1 vehicle. So what I'm really trying to solve is something which is non-convex and choose an exponential size policy. We initially didn't think there was much hope of doing this, but then surprisingly it turns out that you can actually come up with a very interesting sort of approximate control policy for this. So in particular, what we showed was that there's a convex relaxation for this problem, which gives state independent prices. So it's a much smaller space of prices. That has to be true if we want it to be computationally feasible. And these state independent prices give us an approximation factor which is roughly 1 plus number of stations divided by number of vehicles. So no matter what the optimal policy is, we have something which will give us a guarantee of 1 plus n minus 1 over m.
So state independent just means that at every station I, when some passenger arrives wanting to go to station J,
there's a fixed
price you're going to quote, no matter where the vehicles are.
No matter where the vehicles are. If there's no vehicle, I'll quote the price, but I'll say, sorry, there's no vehicle. If there is a vehicle, fixed price.
Right, but there's no rebalancing, the drivers don't get any...
At the moment, I'm not considering rebalancing. Come back to that. She wants to Antonio. Yeah.
2 quick questions. So you said that objective function is concave.
No, I just said this piece, q times I of q is concave. But the problem is this indicator over here actually breaks down the concavity. So the fact that I need to condition on availability actually breaks the concavity.
Okay. And the other question, and that performance guarantee is number of stations.
Yeah, so I agree. I don't know what would happen if you take finer and finer partitions, which is what I think you're going. I think that's an interesting open question. Like, what is the right granularity of doing the prices? In practice, if you saw the picture earlier that I showed, there is a certain granularity which is chosen for just engineering reasons, but it's unclear if that's the optimal granularity. I think that's a great question.
I mean, but if you take that ratio to be a constant,
Oh.
and then let the number of vehicles scale to...
Yeah, so what I think is nice about this is that it's the right sense of parameterization. So it sort of intuitively captures the fact that as I have more and more supply, I get closer to optimality. So it's stronger than just saying this is too approximate or something. It's saying that in a natural sense, as I increase the number of vehicles, the number of stations most probably doesn't change. It actually gets better. There's also an interesting thing which is not obvious in this, but if you scale both the demand and the supply, so if you look at a sort of conventional fluid limit of the system, you can still show this approximation factor goes to 1. This was not known for the system. So even a fluid optimal policy was not known for a closed queuing system until a recent result of Jim Dyant and Braverman and Lei Ying. But in some sense, we get an elementary proof of that fact without constructing the fluid. Complete aside, but there is a sort of very strong sense in which this is really the nicest sort of approximation we could hope for the system. Yeah.
This is with a constant demand rate, right, at each node. So does this suggest that, because I mean this constants, you know, as we heard in the previous talk, you sort of get periodic effects. That suggests that the main difficulty doesn't come about due to, you know, it's not due to the static demand pattern you face, it's more due to the cycling behavior over an outer time scale.
So I'm actually going to argue in a few minutes that, so it's definitely true that the time varying nature affects things. I do think a lot of, like you can get some sort of weaker guarantees under these policies, but in some sense I think this is the right style of policy, even if you have time varying. So what you do is you resolve often enough. I would argue the bigger problem is that these policies need to know all these parameters, which are just much harder. Like, I think that's the fundamental bottleneck, and that's what I think pricing gets around. But yeah, do our guarantees extend to dynamic or to time varying arrivals as is? No, there's some gap there. Okay, so I want to give a brief sense. Oh, sorry, there's a question. Yeah, sorry.
So the state independent pricing policy means like you have flat pricing?
I have a flat price for an origin destination pair during a period of time when everything remains constant. So if my demand changes, I'll change the price. In some sense, if you really believe that demands stay fixed on average for a 3-hour block, I'll have the same price, and then the next 3-hour block, I will change the price. Within that block, yes, it's a flat price. I'll come back in a bit towards the end about what you can do with state dependent, but yeah. It's even surprising for us, like there's a sort of non-trivial existence result here that such a good policy even exists with state independent prices. That wasn't obvious to us when we started. Okay, so how do we prove something like this? Just very briefly. So what we did was essentially we came up with this idea of what we call the elevated flow relaxation. It's essentially a convex program for that problem which gives a valid upper bound while encoding certain conservation laws. So if anyone has seen things like sort of airline pricing, this is sort of similar to looking at a fluid model of the problem, but with some subtle differences. So the non-trivial part, and I'll talk briefly about this, but the non-trivial part is to try and connect this relaxation to the problem with, like, to the actual problem. And what we can do is, we can do this in 2 steps. So we take this relaxation and then we sort of imagine a world where we had infinite vehicles and then show something about like the tightness of these policies in the infinite vehicle system. And then we argue how much do you lose for every vehicle that you remove. So like what is the gain per vehicle that you get? And by sort of combining these, and the fact that there's an upper bound, we show a result. Now, so what is this flow relaxation? And I would argue the flow, if you think a little about it, this is sort of natural, although it took us a long time to view it this way. So what's going on is I'm trying to choose some set of Qs, some set of like admission rates as a function of the current state in order to maximize this ugly looking thing. But I've already argued that this Q times I of Q is concave. So a sum of concave functions is still concave. Now suppose some oracle came and told us, hey, this is the optimal Q star. And in particular, this is the optimal sort of average admission rate between I to j. So this is the vector of average admission rates for this entire system. What I know from Jensen's inequality is if I just sort of put in the average admission rates, then I get a valid upper bound for this. So there's nothing so fancy. If you just look at the fact that this is concave and somebody told me the optimal solution, I know I have an upper bound. And now I can say, well, instead of doing this, I could just maximize over all sort of vectors of admission rates. And the nice thing is this is a concave program. There's just a maximization over a sum of concave functions. This turns out to be 2 weak. So okay, there's a convex program because it's a maximization of concave objective. What's sort of magical is that you can then add a bunch of additional constraints. In particular, you can add these sort of what we call circulation constraints and something which encodes Little's law, and show that once you add in these constraints, these are just linear constraints, then you get a convex relaxation which actually gives you that guarantee. And this step is sort of non-trivial, but it's kind of clear that this is the natural relaxation that you do for this problem, but you kind of needed to sort of do this weird go to infinity and back to show that this works. Not going to go into more detail, but sort of if you combine, the short thing that I wanted to say is that this is really the natural convex relaxation that you would consider. You would just try to maximize overall admission rates while ignoring the fact that there are these weird cross linkages. Ignoring the externalities completely is not, it doesn't work out, but you can sort of add in some minor externalities and still get away with it.
So just, the circulation constraint is almost this critical thing, right? Because it's basically saying that I have vehicles when I want them.
Yeah.
Because what's going on is coming back to me.
Yeah, exactly. So you don't have any sort of sink or...
No, but that's also where you, that's right, but also where the sort of time varying thing where, stuff goes into one place in the morning and, accumulation effects are not there.
Yeah, completely. That is the place. But if you have the
driver's side pricing where voluntarily they will have a reason to go back, right, that might be the...
That might fix this.
Otherwise, this just feels like you've just got circulation for free.
Yeah, so in practice, I think yes. I'm unclear if you can prove something theoretical. So we have some ideas how to extend this partially to time varying, but...
Because right now, the way you have, you have M stations and vehicles, and each one stays at, when they arrive at a new station, it stays for some exponential time, and then goes to some other state. That's the Markov chain.
Yeah.
Now you can solve for the whole thing. But it's not triggered only by external arrivals. If you have a user price dependent thing, that's still a Markov chain, isn't it?
Yeah, so if I understand what you're saying if drivers were allowed to exit or join the system when I violated this condition, I should be okay.
You will get the circulation.
I think that's true.
That might take away from your reward because you have to pay this guy to go.
Yeah, so I don't see a way of proving it, but if you ask me, should you implement something like this? Oh, totally. I mean, Chris, we should implement this. Yeah. I think this is the right way of thinking about these problems. There's a sort of natural reason why it should work out, but it's kind of pleasing that you can show some formal guarantees as well. Yeah.
Just a quick question. So you call it a relaxation. So why do you call it a relaxation? Because of Jensen's inequality, or
because I don't know what this Q star is. So I'm just saying now I'm going to maximize over all possible admission policies, but then I may not actually get the correct flows. So for example, one such Q would be send everything from I to j and nothing, like turn off everything else. But then I don't really have the supply to get this bound. So I'm sort of ignoring the availability constraint. That was the non-convexity, which...
But if you add the circulation constraints, that doesn't change convexity, right?
It doesn't change convexity, and it sort of prevents me from doing these weird policies. That's sort of the intuition. Why that is the intuition why this is kind of the right constraint to add.
But if you had that constraint to begin with, just add it
even
to the
then,
problem up at the top.
Yeah, so maybe another way around this is you could ask that, okay, are we missing something? But you can show that this is tight. There are instances where we get exactly this bound. So, I mean, putting all this together, we can show there's a bound of m over m plus n, and this is fundamental. Like there is a very simple example where our policy does give m over m, where you can actually construct the optimal policy, and we are off by this factor. So it truly is a relaxation. I can sort of write it offline, but we're fairly confident this technique can't go further than this.
And that's without the circulation constraint?
No, with the circulation. So with all of this, we cannot beat m over n plus n. If you don't buy into the stochastics, ignore it. The short summary of what we've done is that even though this is a really messy looking logistical problem, there's sort of, okay, what at least I think is a fairly intuitive way of thinking about like policies for this, which are approximately optimal. And we think you can extend it to certain more complex settings. So you can add reservations. That one turns out to be fairly easy. It works if you have multiple objectives. So if you want to do something like maximize revenue subject to a bound on blah, that stuff turns out to be like subject to a bound on welfare. That's still a convex program, and everything works out. You can do this for dispatch, rebalancing, combinations of those. Just because it's so simple in structure, all of that works. To an extent, we think there's some ways of extending it to like pooling and reservations, but there we do know there are gaps, and we're kind of losing out a lot using this technique. But it's still sort of a pleasingly unified way of thinking about the logistics, or at least like a first approximation to optimizing the logistics of these systems. And for me, the really big thing is, where do we get these parameters? So where are we finding out these demand rates and price elasticities? So what I'll try to argue in sort of the next 20 minutes or so is, this is where I think market mechanisms come in. So what market mechanisms are doing is they're not sort of fundamentally making these systems better in a certain way, but they're sort of taking away the burden of trying to learn and estimate these parameters exactly. So before I move on, I mean, any other questions about this part? Okay, so oddly enough, I'd actually done the work on pricing before I did this. So this was work with Carlos Riquelme and Ramesh Johari. And the reason we got really interested in ride-sharing in the first place was, so this was a quote by Preston McAfee, who is the chief economist at Microsoft. This came out in 2015, and what Preston McAfee is sort of essentially arguing for is that market design in some sense is going to get more and more important in pretty much all walks of life as we move forward. And his feeling was that 2016 would be the year when Silicon Valley recognized that the great value of ride-sharing was the marketplace, not the data. It's unclear to me if that's happened or not, but I mean, Uber and Lyft definitely do have a lot more sort of economists and econ CS folks in the firm. But and the reason we get really excited about thinking about ride-sharing is it's kind of unique amongst all marketplaces in that the platform sets the price. This is really not true for pretty much any other marketplace. So if you think of, say, Airbnb or Etsy or anything of that sort, any of these marketplaces, they act as a board, like a message board where buyers and sellers sort of negotiate prices, or sellers set prices. And ride-sharing somehow went around this with this sort of bold decision to just set prices. And there were ride-sharing firms which experimented with letting drivers choose their prices. They don't exist anymore. So in some sense, it feels like this is the right model for ride-sharing. And in some sense, what we were intrigued by is, why is this the case? So what is dynamic pricing and the ability of the market to price in these platforms? What is it buying? And essentially our kind of short answer is it's not buying something fundamentally compared to static pricing, but it's buying this ability of an algorithm to self-calibrate, to find the right parameter settings without actually learning the parameters. So what do I mean by this? So here's kind of the underlying conundrum that we had. So if you think about, or if you just look at the rates, the request rates within certain hourly blocks, so the sort of diagram David was showing, these are definitely time varying, but they're somewhat predictable. Like they vary in fairly consistent ways. So if you look at the data in the morning, people are trying to come from the suburbs into the center. If you look at it in the evening, they're going in the opposite direction. There's a kind of intuitive underlying trends which exist in fairly persistent fashion. So the puzzle is in some sense not that why not do dynamic pricing? But why not just have like a schedule of rates? Why not say these are the rates you have for different hours of the day, and then just keep it in place? You're not going to have people complaining at Uber for doing surge pricing, etc. It seems like it solves everything. We have all this data. Why not do hourly prices? And that's sort of what I want to understand. Like, what is the difference between making prices depend on the instantaneous state versus making it just depend on what happens over a few hours of time? And I'll use basically the same model as before to try and understand this question, but the big simplification I'll do is I'll just focus on a single region. So I'll focus on a single station, and in some sense, I'll think of all other stations as like the net effect of cars coming from other stations as being sort of averaged out into a flow of cars. You'll see this in a second. But as before, I'll assume all the system parameters stay the same, so the arrival rates stay the same, and I can still charge a price which is a function of the number of vehicles in the station at the moment. I'm not looking at the number of vehicles at other stations, just the instantaneous number of vehicles in the current station. How many vehicles are there in this neighborhood? This goes back to your question. I'm going to assume that you earn a fixed fraction of every dollar spent. This is not essential, but okay. In some sense, for the results extend, but they will become messier if I don't assume. And the sort of more crucial assumption is this one. So as before, my passengers are still myopic. They still react to the instantaneous quantities. But I'm going to think of the drivers as sort of making decisions of whether or not to work on the system based on a sort of long-term sampling of the system. So think of it as I'm trying to decide between working as a freelance web designer or something versus working on Lyft or Uber for a certain amount of time. What I'm thinking of the drivers as doing is they kind of try out the system for a few days and see, am I making enough money or not? Is it worthwhile? Is it worthwhile? Is the sort of the cost worth it in terms of doing this work? And once they do this, they make a decision. Do I want to work for Lyft or do I not want to work for Lyft? Like, what time do I want to work? Where do I want to work? And what this means in terms of the model is I still have a sort of similar birth death process of cars at a station as before. So these are the number of cars which are increasing, and I'm saying the cars are increasing at some rate lambda. This just aggregates all the cars coming in from outside and from other places. But I've set these prices, and in particular what I've done here is I've selected a threshold. I have a low price higher than that threshold and a high price lower than that. So what it's going to do is when there are a lot of cars, I have a low price, so I'm sort of trying to push the system down, and then when I have very few cars, I'm deterring people from taking these cars and push the number of cars back up. So that's what happens for the passengers. This is what's new in this model, which is the way the driver thinks about it is, I'm thinking of there's a sort of potential flow of drivers. I think of there's this potential population of drivers who could join. Each one has some reservation value. There's some magic number for which they're going to work on the platform. And they have this amazing simulator, they simulate the system, and they figure out how much they would earn if they join the system. And then they decide whether to join or not. So they're making this decision based on, they have this reservation value, they're looking at the sort of long-term earning from the platform, and they're deciding whether to join or not. The problem, of course, being is that this is sort of inducing like an equilibrium system. So the amount of money they earn and the amount of time they spend on the system will depend on who decides to join the system. And what we want to understand is what is the equilibrium of this when we do dynamic pricing. A bit of a mouthful, but any questions about that? So that's the question that I want to try and understand. You could argue that, okay, why is this fact that drivers look at a long-term figures valid? There's a sense in which all the ride-sharing platforms actually try and encourage drivers to do this. So they give these kind of weekly summaries. This is again from a few years back. But essentially what both Lyft and Uber give is some sort of weekly summaries of how much money you made, how much money you would have made if you worked at some other time, at some other place, etc., etc. So you are sort of encouraging the drivers to do this kind of what-if analysis and decide what is best for them. Yeah.
So are driver costs explicitly called out?
I'm kind of...
Drivers? Are they well understood?
Not by me, and I'm sweeping that under the rug. Do Lyft and Uber understand that? I genuinely don't know.
If there's a relative question relative to, say, transport companies that do have a reasonable understanding of their costs.
Yeah, so in some sense, both the benefit and the weakness of the market is you don't care. The market is what the market is. The drivers decide whether it's worthwhile for them, but that's kind of skirting around the topic. But yeah, no, I completely agree. So I'm assuming that, I'm sweeping that under the rug. Okay, so this is sort of the equilibrium system that I've set up. I'm setting these prices which depend on the number of drivers. This leads to a steady state system, steady state of this queue. The driver looks at the steady state and says, okay, this is how much money, this is the hourly earning I'll get. This is how much money I earn. This is how much time I spend on the platform. They then compare it to doing whatever else they would have done, and they decide, is it worthwhile for me or not. I want to try and understand what's the equilibrium of this. This is messy enough that, we can show existence and conditions for uniqueness. There's no closed form for this. There's no hope of getting that. But it's one-dimensional. So if I had just a single price, this is just a one-dimensional problem, I could just search for the equilibrium. That's what I've done here. And so the sort of nice thing that's happening is as I increase, so I just have a single price, this is static pricing. As I increase if the price is 0, drivers are not earning any money, why would they join? As I increase the price, drivers are getting happier and happier. At this point, what's happening is now the passengers are upset at the price, and so the time between each ride is blowing up. And so the driver is saying, okay, I'm working for 3 hours, but I'm not getting enough rides. When I get a ride, I get a lot of money, but it's not worthwhile. And so even though I've not built in stability into the model, the stability of the queuing system itself is just implicit in looking at for this equilibrium. It has to be stable. And you can play the same game, but what I'm now going to do is I'll take these number of drivers, or the arrival rate of drivers and the arrival rate of passengers, and scale that. So I'll just say, what happens if the system becomes 10 times bigger? Then I get a curve which looks like this. And I can keep doing this game. What happens if it gets 100 times bigger? I get another curve. And it feels like it's sort of approaching something. And then the nice thing is that we can actually characterize exactly what it approaches in the limit. And it turns out that in the limit, the equilibrium goes, or this equilibrium rate of rides converges to the minimum of 2 functions, one of which only depends on supply, one of which only depends on demand. So if you were an economist and you kind of looked at it in this direction, what you would see is a demand-supply curve. But I didn't assume a demand-supply curve. I sort of assumed micro foundations and built up a demand-supply curve.
What's on the vertical axis?
Good, sorry. So this is the rate of rides that I get in the system divided by the scaling parameter. So the normalized rate of rides. But you could do this for revenue or welfare. You get something similar. And this is the single price. So this is, okay, so why do I like this? This was kind of the point at which we thought, okay, this model has some legs. Like, it makes sense. It's not giving something nonsensical. So we can use this to start asking what happens if you do dynamic pricing. So what if instead of a single price, I had 2 prices and this threshold for when to switch between the prices? Okay. I seem to have removed the figures, but you can play the same game in terms of looking at the scaling behavior, and you can again exactly characterize what happens with dynamic pricing in the limit. So remove the scaling pictures, but in the limit what you can show is it's not going to be the same as just having a single price, but interestingly, the maximum rate of rides that you can get is identical under dynamic pricing or static pricing. So even if you sort of optimally choose these 2 prices and this transition point, the optimal thing to do is actually to have a single price, which corresponds to the optimal static price. And under some conditions, you can prove this formally. So assuming a certain, a certain distribution is regular, the rate of rides for any dynamic pricing policy with 2 prices and a single threshold is less than equal to that under the optimal static pricing. Every time I give this talk, or there's a sense people feel that this is perhaps obvious. It'll take a few seconds to convince you that this is not unobvious, but it's not completely trivial. So there's a sense that if you're taking this limit, maybe there are no fluctuations in the limit. Like maybe in the fluid limit, there is no randomness, there's no different, there's just a fixed number of drivers, so I'm seeing a single price. Actually, that's not true. So what's happening is because I'm also changing the point at which I flip between the prices, what happens is in the limit, every time a passenger comes in, they sample from a IID distribution of cars. So they sample 5 cars, 10 cars, blah, 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 and then there's a fixed parameter which decides how much they have to pay. It's not obvious, but you can show that. And there's also this is kind of remarkably similar to these sort of similar results in revenue management. So Gallego van Ryzen, etc., which say that under certain limits, static prices are optimal. But that is actually also not true here. So if I remove this assumption, like for example, if I have a mixture distribution, you can show that a dynamic price does strictly better than a static price, even in the limit. So there's the closest parallel that we found to this in sort of existing literature is there's this literature on kind of market segmentation in like large markets. Like when is it beneficial to segment a market into multiple parts or segment buyers into two parts versus sort of not segment them. And there you kind of get qualitatively similar phenomena. And in some sense, what we're showing is under this sort of queuing model, you get similar conditions as these sort of market segmentation problems. But it's also a little disappointing because I kind of promised you that dynamic pricing is really important, and this seems to suggest that it's not. There is this amazing static price in the sky which would have just optimized everything.
I'm not certain I understand. The vertical axis here is the ride rate.
Yeah, so this is the rate of rides, this is the revenue. This curve here. So
that's
this is the revenue.
Oh,
yes.
okay.
Yeah, so but this is kind of fairly robust to what you can look at welfare, and there's a sort of similar thing.
No, that's what I wasn't.
Yeah, sorry, I should have specified.
This also coming, like you assume the fixed arrival rate or something. I thought the point of dynamic pricing is that they react to
Changing arrivals.
changing arrivals.
So my claim is, so that's true and that could help, but then the thought is perhaps arrivals don't change that fast. But really, I mean, dynamic pricing is reacting to instantaneous scarcity in some sense. Like, are there enough cars or aren't there enough cars? Okay, so one way of thinking about it is, yes, so if I'm not going to claim that these will hold as is if I have changing arrival rates, but there's still a question, suppose we don't have changing arrival rates, can we show that it's doing something interesting? Like, what is dynamic pricing doing? It's not this.
No, but there's another possibility, which is, for a given arrival rate, there's a price, that's static. As you change the arrival rate, the price is changing.
Yeah, so I think what Eva's saying, it's changing almost instantaneously, and so the dynamic pricing tracks that.
Okay,
It's that.
I'm not saying that right now, but that's definitely, that statement is true. And so maybe it's a mixture after you solve for this,
Yeah.
then there's some lookup table which says if the arrival rate vector is this, then impose this
Then
price.
it uses this static price. Right. So that's what this would suggest you should do. My argument is the big weakness in that is, do I really know that arrival rate exactly? And kind of one way of formalizing this, I could ask the question, okay, how does my performance change if I have some uncertainty in these parameters? So is this prediction I made robust to knowing this arrival rate exactly versus having some error? And that's kind of what we did. So we said, okay, so what if you had like a demand shock? So what if I didn't know the exact demand, but I knew it up to like plus minus 10%? So this would be the optimal rate that you'd get, or the optimal, in this case, rate of rides, if you knew the exact quantities. But what I'm doing here is I'm assuming at some point, and then trying to just fix that static price and see what performance I get. And what's happening here is your performance kind of falls off a cliff. Like you do really badly as soon as you have some uncertainty in either direction. Does that make sense of what I've done here? So I've said, I'm assuming there is a certain set of parameters. I solve for this amazing optimal price. I implement it, but in reality, the parameters were slightly perturbed. And this is the optimal rate I would have got if I knew the parameter. This is what I get if I just fix this single parameter. Now, on the other hand, what I could do is I could say, well, maybe I know I have this uncertainty, so I know I'm within plus minus 10%. So I know this number mu naught is anything between 3.6 and 4.4. And I can use that to set up the two prices. So I can this is my pessimistic price because it's like my optimistic demand forecast. This is a pessimistic demand forecast, so I set a high price. And if you do that, what you can show is that like under dynamic pricing using that policy, you're actually very close to this optimal solution. In particular, formally what you can show is the performance under dynamic pricing is always better than like a linear approximation of this optimal manifold. So if I sort of select a set of breakpoints, draw a linear approximation of this curve, dynamic pricing will always be above that. And I could do it with multiple such points. So I could say I have like 6 prices which I arrange in some order. In some sense, what it's doing is it's kind of getting this nice linear approximation to this optimal curve without actually knowing the parameters. And you can formally show that this is true. So there is a kind of intrinsic robustness which is built into dynamic pricing. So it does not need to know the parameters exactly, but because it can react to the changes, in some sense, in underscaling, the changes happen fast enough that your prices calibrate. Correct.
Do you have any idea on like how much the drivers are responding to?
Yeah, so no.
Maybe that's the problem that dynamic pricing is solving, is changing supply rather than, repelling the demand.
I think that's not, I mean, that's definitely true to an extent, but I think that can't happen fast enough. So if there's like a increase, it's going to take like 15-20 minutes for a driver to react to that.
I agree with that. But in the model that you started with, your driver it can go from state I to state J essentially instantaneously on empty count, right? And so the model may have got there's no hysteresis built in.
Yeah, no, that's fair. So I am not, okay, so I'm not looking at that at all. It
So
could
you could add the
be,
hysteresis in simulation land and see if this statements are robust enough, right?
yeah, I should. I don't know, there's a very particular proof technique I use which I know will break down there, but which is not an excuse for not having done that. But yeah, I agree. So I'm not claiming this is the only effect. I am trying to convince you it's quite a surprising effect. Like we did not expect it to be such a good approximation, and there is a very good sort of explanation as to what's going on. There does seem to be a sort of intrinsic robustness to these policies, which at least I feel is kind of the stronger reason why they seem to work so well. They're not fundamentally better, but they have this inbuilt robustness. Now, is this something which I'm validating using data? No.
No, but I'm saying that simulations would satisfy me, right?
I'm pretty sure the drivers react to some extent. So one thing I did assume is that drivers, I hid this, but I assume drivers exit the system without looking at the price, just probabilistically. I think if you relax that and say they look at the price, and if it's high, they stay, that'll be a second order effect. But I mean, we did some simulations for just that, and that was second order, but yeah. I agree that's something that's not very well. But okay, so that's kind of what I was suggesting, that what I think the market mechanisms are buying in these platforms is not necessarily that they are better than kind of static pricing, but they seem to sort of buy this intrinsic robustness. They buy this sort of lack of sensitivity to like getting your estimates wrong. So I think Ramesh was saying that he likes to quote it as saying that you can either trust your data science team a lot, or you can trust dynamic pricing. We, in some sense, are suggesting trusting dynamic pricing is the way to go. But completely, I mean, I'm not going to claim this answers everything, but it's sort of intriguing as to, it's not the usual narrative of what's going on in these platforms, but it's, I think, a fairly strong suggestions as to something of this sort is going on.
Quick question. So the supply of drivers you showed us earlier, so given a static price plan, that entire price trajectory would determine the supply of drivers. Is that?
It's more the average under a price trajectory. So I set up the price trajectory, the system reaches some equilibrium, whatever I get under that, the drivers look at the average and decide whether or not to look. So they're reacting, but they're reacting to sort of the smoothed out version of the trajectory.
And that same response is used for dynamic pricing as well?
That same response is used for dynamic pricing.
Okay. And can you remind us that dynamic price is a function of?
The instantaneous number of vehicles in a region. I look around me, if there are 5 vehicles, I charge you something. If there are 10, I charge you a lower price.
So if you have a large network with many locations, this could be a function with a very high dimensional domain.
Yeah, so instantaneous price only of your neighborhood. You ignore other neighborhoods. You only look at your neighborhood. It's a local instantaneous supply. So it is just one dimension.
So you don't care where the cars go to when you send them from A to B?
No. I'd like to argue in a weak sense that the two parts somehow argue that you should decouple them, but yeah, in this model we don't care about that. That's fair.
So as far as I know, Uber and Lyft provide some kind of incentives to the drivers. I mean, so that the drivers, are available for a certain amount of time during the week, etc. So how does all that play out into this? I mean,
I have no idea. That's why I could try making up stories, but I don't have a very clear answer to that. So so what happens to other driver incentives? How do they sort of play into this? It's unclear. If you talk to an economist, they'd usually suggest that there's a sense in which you shouldn't even have those incentives. The right thing to do would be completely insulate the drivers from these marketplace dynamics. It's not being done, and it's a really interesting question as to how these different pieces mesh together. I think this is a very interesting set of questions, and just the driver incentives. It's a good segue to come to what I think are the interesting questions. So just maybe 5 minutes? Yeah, okay. Oh, 10 minutes, yeah. So what I sort of showed up till now was we have these models which I think are good models for these systems. They sort of set up fairly non-trivial problems about solving the logistics and the pricing, but we have now some handle on how to do it in certain approximate senses, and you seem to get certain strong signals as to why these pricing mechanisms and these sort of simple flow models seem to work. So that's kind of the state of things as they are. So one question, I think this is what Dilip was pointing out, what do we get if we switch from state independent to state dependent? So as I was saying, we kind of have a counterexample which shows you cannot improve on our result, and that counterexample actually works even if you do state. I think there. Okay, I'll take that back. But there is a very strong sense in which we have counterexamples which show you cannot, even if you did state dependent, you can't get better than this m over m plus n compared to this convex relaxation. The relaxation is just too weak in certain regimes. And this is sort of, okay, for those of you who've seen these models in revenue management, there are certain regimes where you get a square root t regret, or in bandit problems. There's certain other regimes where you do much better. And there's sort of similar phenomena which happens here. But it turns out for just the dispatch problem under a certain Beaker assumption called complete resource pooling, you can improve the result and show that you can get the suboptimality to actually decay exponentially in m. So instead of 1 plus n over m, you can get something like 1 plus a constant times e to the minus m, or e to the minus theta m. But we don't know anything about the constants. We just know this in what's called the large deviation sense, that you can show there's an optimal policy. The optimal policy is state dependent. It's actually fairly non-trivial to even construct what it is. So this was joint work with Pengyu Chan and Yash Kanoria at Columbia. But we could show what the optimal policy is. It looks something like what's called a shifted max weight policy, but you can prove that it gets exponential decay. So initially this policy may be better, but in sort of a large system, that policy will be better in general. I've not dealt at all with bursty arrivals. All my models have Poisson arrivals. It's a very natural question, what happens if you have bursts? And this is, I think, a really meaningful question. I would argue this is a first order effect in any of these systems, just because of things like train stations or games getting over, or concerts or things like that. And just what are the right policies for bursty arrivals? I don't have a great idea. I think that's an interesting problem to look at. Non-stationary as well, although I think bursty is sort of the right, sort of the point at which you will get interesting first order effects. One other question, okay, can we sort of, yes?
Small comment. See, that's one of the cases where the data science team may have something as a leg out. We did something where for the New York City data taxi, there were some events in Jacob Jarwitz Center. So if I give 500 rides, I don't know what it was. If I give 500 rides in, I expect to give roughly 500 rides out at a certain particular known time when the event finishes. And we found that this was true, not just there, but some other cities where we had data. So especially event-based, they will know better, right?
No, I agree. And if I get what you're saying, you're suggesting that you should handle these outside the system in some sense. You should.
use data as well.
Yeah, you can use data, predict this, and then somehow like maybe do reservations in advance to smoothen this out. Yeah, so that's what I think is the interesting thing. That dynamic pricing alone is the wrong way to target that. You need an additional sort of lever to target that. And what is that lever? I think is a nice question.
Some of these guys, whether they're coming off a train or an event, they know they want
Oh yeah, I mean,
service.
I start checking.
It's not news that your train will arrive in, like you're driving in the train. You know that you're almost there. It's not like...
So I do things with Lyft allows reservations now, right? And so you can do advanced reservations. You can say, I think I'll arrive in 10 minutes, blah, 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 and so reserve for that, which I think is the right way to go about it. But yeah, just in some sense, I feel there are interesting mechanism design questions there with that. And then that sort of segues into this, like how do we kind of use these tools to think about reservation? Like I think that's really interesting. This is the same thing David sort of brought up. Like I think reservation mechanism, it feels somewhat old school, but like it's coming back. It's going to be back in fashion. Like Lyft has this interesting thing where, correct me if you still have it, where you can reserve your morning commute. And the idea is that you can sort of do this commute with someone else and sort of reserve it the previous night. Is this right, or am I making this up? Okay.
You tried it.
Yeah, you tried it and it didn't work. Okay. So that's even more reason why we should be thinking about these problems. It clearly doesn't work exactly as we would expect. So, but I think reservation mechanisms are a really interesting thing to think about.
I don't work for Lyft or Uber, but you can definitely say that in the city you live in, it doesn't work. Which just happens to be my city. It's not working.
Ithaca is a bad example to think about scaling in systems. There is no scaling.
I mean, it's because the student drivers, Lyft consists of student drivers.
Because the population of the town is 30,000. Everything is 10 minutes of each other. So yeah, there's no intrinsic scale in.
Demand way exceeds supply, and there's no reservation available. Like they just don't have it in the system.
They don't have reservation.
The reservation is not allowed, and generally demand exceeds supply by a long shot, and that's true both for Lyft and Uber.
Yeah, I mean, at the moment there aren't rides. Ride pooling is one thing which I think is really fascinating, just from a kind of combinatorial optimization perspective, this idea of sort of combining these rides in some optimal way. This is something like, if you ask me what's like the one problem I'd really like to work on, I think even when I'd stopped working on this project, like I always thought ride pooling was the interesting one. It does feel like it's having a huge effect. Like I get cheaper rides for sure, and if you take Lyftline, if you all haven't tried Lyftline or Uber Pool, like there's a marked difference in the rides. It feels anecdotally that the fraction of people getting matched up is also increasing. It feels like a win-win for everyone. You get cheaper rides, there's less pollution, blah, 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 but they're just nice problems in thinking about that. We've been thinking a little about it, but again, there's not much known. Okay, where can we go beyond this? Just talk about like maybe a few more things which I think are interesting, and like, hopefully we can work on over the semester. So one is the impact of platform competition. Now this is a problem which in some sense only the academics would care about. The platforms care about it, but will they really try to work in some formal way on this? I doubt. There are some hidden interests. But this is something which I think is really important, not just from a game theory point of view in terms of just competition between two platforms into a duopoly model, but just what's the effect on society of having two competing platforms providing the same service. So we started thinking a little bit about this. So this was joint work with Thibaut Sejourné. So he's actually an undergraduate student or master student at the École Polytechnique, and my colleague Samita Samaranayake. So what we were looking at is a very simplified model. So sort of similar to the model but we've been looking at. But what I want to understand is what's the cost of doing this optimization in a decentral manner. So what do I mean? I'm imagining a world where there's either a single platform, so the Singapore government controls all of ride sharing, versus there are two platforms which are operating. And I'm thinking of these two platforms, they're not competing with each other, they've just completely partitioned the space. So people who are younger choose Lyft, people who are older and richer choose Uber, or make up your own stories, but in some sense the world has got partitioned into Lyft users and Uber users. And what I want to understand is, and each of these platforms, the only control lever they're using is just rebalancing. They're rebalancing their empty vehicles, and they're trying to do this as best as possible to try and minimize cost while serving as many people as possible. what we wanted to understand was, like, what's the price of fragmenting the market into two pieces? So what's the price that we incur when I go from a single platform to sort of solving two separate optimization problems, when the demand is getting partitioned, but it's sort of getting randomly partitioned. So what's the difference? In some sense, there's this one convex program we're solving. What happens to this problem when we split it into two convex programs with random inputs?
Good question. You assume that the same driver doesn't work for both?
No, yeah. So the way we were thinking about it is, this is the future with autonomous vehicles. Both firms have their own forms of autonomous vehicles. Everyone is in Team Lyft or Team Uber. You've made your decision. What's happening to society?
So maybe we should let him finish, because the time is almost running out, and then have questions at the end.
Yeah, okay, but I have like one more slide. So, okay, what happens here, it's somewhat surprising. So what it turns out is you actually get a phase transition. So it turns out that depending on what the underlying demand is, if the underlying demand has a certain structure, then you actually, when you scale up the demand, your suboptimality decays to 0, whereas in some other regimes, your suboptimality actually goes to infinity. And the interesting thing is, this is in some sense not academic. If you look at the New York City data and sort of apply our criterion on that, you actually see this regime show up in certain hours of the day. So you get roughly 10% of like blocks of time when the system appears to be in this state. So we are imagining the New York City data as being the centralized platform, and then trying to think of what happens when it gets split into two pieces. And it seems like you could get these effects. So in some extent, I'm not claiming this exists, or that we do think this exists to some extent, but it's also the higher level point being that you can get really interesting effects in these problems just because of the underlying combinatorial nature. So even something as simple as what happens when you have two platforms competing is not an obvious answer. So there's sort of few other questions, I'll kind of put these up, which I think are worth thinking about. So one of them is this thing I've been sort of harping upon: what is the value of information? Like, how much do we buy from forecasting versus how much do we buy from having algorithms which in some sense self-calibrate? And there is some really, really nice work recently on thinking about this for what's called the switch scheduling model, where you don't need, there's this certain algorithm which we've known for a long time, this thing called max weight, which you can prove kind of does this self-calibration in a very, very strong way. It's kind of optimal in a very strong sense, and I'm kind of intrigued by, can we kind of come up with other algorithms which do this? So are there algorithms for this problem which sort of quickly self-calibrate when the parameters change? And can we prove something formally about like how fast they do this? I think this is a really important question, and I mean, it's not clear what's the right way to attack it, but in some sense, it's less about how does ride-sharing affect public transit, but more how can it sort of help public transit. So there is a sense that there are inefficiencies in public transit, so in particular things like the last mile problem, and there it feels like it's not obvious, at least, that whether when you combine the two, if it's like submodular or supermodular. Like, do you get benefits from combining the two, or does it hurt each other in equilibrium? But it's clear that the policies must change. So at the moment, the two don't talk to each other. But what is the right sense for the two to be talking to each other? Can we sort of start answering that? And again, this is something where I feel academia may move first before the platforms really think about this. This is kind of even further out, but just like there are a lot of these articles now about like what is the role of like a freelance worker in kind of society in general. And like my way of framing this in the context of ride sharing is what is the right mix of like people that you employ to drive, freelancers, and coming up soon like autonomous vehicles. Like, should you have a completely autonomous service now? What happens to all these people who are earning money? Do you introduce them in small numbers? How do they work with each other? Again, something where there's going to be some amount of modeling, but I think we are at a point where we can start thinking about some of these. So I hope to do that over the semester. Sorry for running late, but yeah, that's all I have.
Thank you, Sid, and I'm sure he is happy to still answer a few questions.
I have the impression that in platform competition, that in China, Didi ate up Uber.
Yes.
So, which is very different from the competition that you showed earlier. So what is the, I mean,
Yeah, so I'm really looking at fragmentation. So I'm sort of saying, so I would like to believe that having, kind of tautologically, having choice is good for the consumers, good for the drivers. So it does feel like it's better for us to have both these services and perhaps even more of these.
no, but I want to know, can you speculate as to why
Yes.
it turned out that Didi ate Uber?
I mean, I think if you start looking at, if I now sort of build in things like people choose which service is giving a lower price, you can maybe come up with fairly simple models where, okay, X started off with at a better position initially in terms of maybe cash reserves, and so they could drive the other company out before coming back.
The same thing happening in Uber versus Lyft?
Oh, I sincerely hope not. Everyone please switch to Lyft. No, it's
How the market is functioning, not what
I don't know. I guess the one thought would be there are other similar, I mean, this seems similar to things like the airplane networks. And we do, to say airplane networks, like again, you could have had one company take over, or say rental cars. In some sense, it hasn't happened. So
I mean, right now, Uber is losing money like nobody's business, right? And I imagine Lyft is also not making money. And so
we
how
have,
can you coexist?
do we have volunteers on this?
No, we can't.
Oh, this can't be on tape. No, okay.
I can't push them to answer this question, but
No, so I mean, I think it's a good question. There's a sense that I don't think I can say something useful about that yet, but perhaps in these limited contexts.
Okay, another question which relates exactly to your setup is you had a number of vehicles, I think it was fixed or with some M or N or something.
Yeah.
And so if the platform can control the number of vehicles, would it increase or decrease? Does the revenue to the platform go up or down?
So that depends on how you engineer, like how much the driver gets versus.
And so if we fix.
Yeah. So I mean, I can give you an answer under this model, but I am hiding the fact that like this is not the optimal spread.
Okay.
I think it should go up, but.
Up with higher or lower?
Yeah, because so the intuitive argument would be I can always throw out certain drivers by making it. So I should always, in some sense, be able to simulate a more restricted system given more resources. So if I do it optimally, it feels weird that it won't go up. But
they don't do it optimally.
No, that's what. So that's what. Like any answer I give.
Would you shrink the
search
supply
price goes up.
or
Yeah. So under this model, what would happen? I don't know.
Can I venture that it depends on the shape of the supply curve?
Yeah.
Like it must depend on the shape of the supply curve. What fraction of the population is how sensitive they're to price?
there, right? So
How
Yeah, but
high do we pushing up the price when we have to put it in multiplier to get rid of some people? How high does the price jump?
So that's
if it
my-
jumps a
Yeah,
lot,
so-
then
that
it
is
must
my
be
question
good to
as to
restrict it.
whether,
Yeah. So.
the monopolies, you'd expect reduced service or greater service or what?
I don't know off the top of my head. Okay, so I think the right way of formulating would be what is the parameter of these curves which controls this comparative static. I genuinely haven't thought about that. Yeah, that's.
Okay, maybe given that we've passed the time, we're going to take other questions offline. I'm sure Sid is around for the next
I'm
few
around.
minutes. So thank you very much.
Thank you.
I too have to give me a first it was one of the